Hello, good evening, everyone. Today is the last class of this doubt solving session of Design of Farm Machinery course, and this is week 12. I hope you have solved all week assignments till week 11 and you have not faced any problem. And today we will solve week 11. Today we will solve week 12 of last year question. And this week mainly covers threshing part of Design of Farm Machinery. So coming to threshing, threshing is the process of separating grains from the harvested crop, and it can be achieved by either striking the ears or by rubbing and stripping. And a rotating cylinder and a concave, this cylinder and concave are the two important components used to accomplish this threshing operation. And the crops are forced to pass through the gap between rotating cylinders. And is subjected to impact, rubbing, and vibration, which causes the detachment of the grain. And the classification of thresher. So threshers can be classified based on three criteria. First is path of travel of crop with respect to cylinder axis. Second is crop bundle position. And third is types of cylinder used. So, Jigyasa, we have just started the class, and I have just discussed what is threshing, and now I am discussing classification of threshing. So thresher can be classified based on these three criteria. First is path of travel of the crop. Second is crop bundle position. Third is type of cylinder used. So based on path of the travel of the crop, a thresher can be classified as axial flow or cross flow. I'm audible, right?
Yes, sir, you're audible. You're audible, sir.
Hello. Jigyasa, can you speak something?
Sir, you're audible.
Okay.
You are audible.
So yes, axial flow, axial flow type thresher and cross flow type thresher. So axial flow type thresher is the one in which the path of travel of the crop is along the axis of the cylinder. See here in this figure, it is shown an axial flow thresher. The path of the crop is along the axis of the cylinder. So this is the axis of cylinder. Here the crop is entering, and it is flowing across, is along this axis of the cylinder, and it is coming outside. So the crop flow is along the cylinder, and what happens in cross flow is the path of travel of the crop is perpendicular to the axis of cylinder. So this is axis of cylinder, and its perpendicular direction is along this. So path of travel of the crop is along the perpendicular of the axis of the cylinder. So this is based on the path of travel of the crop. Second is Second classification is based on the crop bundle position, where first is hold on type, second is throw in type. So hold on type is the one in which we hold the crop and hold the crops, and the thresher threshes the crops. Throw in type is one in which giving the we are not holding the crop, we are just giving it inside the thresher and it is being threshed. So third classification is based on the type of cylinder. This is one of the most important criteria of classification, which will be discussed in whole chapter here. So first cylinder type is drummy or hammer mill type. So here it is an example of drummy type or hammer mill type. It consists of beaters. These are the beaters which threshes the crop, and this is a drummy type. And when in this drummy type, if we are providing aspirator along with this setup, then it will become hammer mill type. So this is the difference between hammer mill and drum mill type. Second is syndicated type. Here the flywheels the flywheel with corrugations is provided. This is the flywheel, and here you can see corrugations are there, and it gives a fine quality of bhusa. So this is the second type. Third one is a spike tooth type. So in spike tooth type there are spikes, as the name is clear, and in rasp type there are rasp bars. So what are the different purpose of this type of threshers? We will discuss it just in next slides. In wire loop type thresher, wire loop type cylinder, wire loops are there. This is mainly for paddy crop. So what you can note down from this from of for this above type of cylinder is that drummy type, hammer mill type, and syndicated type thresher are suitable for wheat crops. So these are for wheat crops. Drummy type, hammer mill type, and syndicated type. These are for wheat crops, and they give fine quality of bhusa. So this point can be noted. And second thing is Raspa type and wire loop type and axial flow type. These three types of thresher are for paddy crop, and they don't make fine quality of bhusa. Raspa type thresher can be used for other type of crops also. So this is a multi crop type cylinder. So Raspa will be used in all types of crops. So next thing is component of thresher. So talking about component of thresher, first is feeding device, second is threshing cylinder, third is concave, fourth is blower or aspirator, and fifth one is sieve, shaker, or straw worker. And feeding devices are also of many types: chute type, trough type, hopper type, conveyor type. And threshing mechanism mainly deals with mainly have three means thresher have mainly three mechanism for threshing. First one is impact, second is friction, and third is vibration. In impact, the impact between rotating cylinder and crop material happens and it threshes the crop. In friction, cylinder material and crop due to rubbing action and between the crop material makes the threshing operation. Vibration of the crop material due to striking of the crop surface at regular interval can also be used for threshing. So these are the mechanism of threshing. Next thing is number of strikes of the crop with bars. This formula can be used. And next thing is parameters affecting the performance of a thresher. So parameter is crop parameter. So crop parameter mainly involves moisture content, type of crop, grain to straw ratio, green matter present. So these are the crop parameters which defines the performance of the thresher. Second thing is machine parameter. Machine parameter involves type of cylinder, type of tooth, concave gap, length of concave. These all factors will influence the threshing efficiency. So and next thing is operating parameter. Here it is RPM of the drum and feeding rate. This is the operating parameter. So these three are the main parameters under which all the parameters will come. So first is crop parameter. So mainly in parameter, moisture content of the crop is there. So here you can see this is the graph plot for moisture content and this is damage percentage. So the first one is unthreshed grain. This is the unthreshed percentage. So when moisture content increases, unthreshed grain increases. This you can conclude from the graph, and this is for damaged grain. When moisture content increases, damaged grain decreases. This is for moisture content. And second one is grain to straw ratio. So this is on this x-axis it is grain to straw ratio. Grain to straw ratio is maximum here. 60 it is on, means if this side more grain is there, this side less grain is there, and this is damage percentage. So if more grains are there in the crop to be threshed, so more grains will be exposed for threshing operation. So damage percentage will increase. So if we are increasing grain to straw ratio, damage percentage will increase. Next thing is effect of peripheral speed of the teeth. Here amount of peripheral speed of the three teeth is there, amount of damaged grain is this one, and amount of unthreshed grain is this one. And this is for feeding rate, amount of grain shifted, amount of damaged grain. In both, in first case, if we are increasing peripheral speed, amount of damaged grain is increasing, and if we are increasing feed rate, then amount of damaged grain is decreasing. Next thing is effect of shape of drum. So this is an hexagonal and this is spherical type drum. So if in hexagonal, vibration will be more in case of hexagonal shape as compared to circular drum. Thus threshing efficiency of hexagonal drum is higher because light has went. So we'll continue the class. Zero- There is a power cut in the campus. So we will continue the class. So effect of shape of drum is there. In hexagonal there is more vibration, so it dressing efficiency will be more. As we have seen that we have seen that the vibration also affects threshing efficiency. So more vibration, more threshing will be there. Next thing is type of tooth. This is an important factor in case of spike tooth also. The shape of tooth and surface roughness of the tooth has a profound will we have a profound effect on the threshing operation. Threshing efficiency of a thresher increases if the surface of tooth is rough. So more rough will be the surface, more threshing will happen. Next thing is effect of concave gap. Slippage of the grain ears from the drum increases with the increase in concave gap. So what will happen? Amount of threshed grain will decrease and amount of damaged grain will also decrease. This is cylinder, suppose this is its concave. So if the gap is increasing, what will happen? If the gap is increasing, threshing efficiency will decrease and amount of damaged grain will also decrease because less crop is being exposed, because less crop is being crushed. So threshing efficiency will decrease at the same time damage will also decrease. This is like complementary to each other. You can just make a thumb rule that if threshing efficiency decreases, most of the time damage grain decreases. Effect of length of concave. Threshing time increases with increasing concave length, thus both amount of broken grain and amount of threshed grain increases. So you can see here again what is happening. Threshing time increases with increase in concave length. Concave length is increasing, threshing time is increasing. So what is happening? Threshing efficiency will increase and damaged grain will also increase. So this goes side by side always. Next thing is effect of cylinder diameter. With a smaller diameter of cylinder, the inlet velocity of crop material is lower in drums with higher diameter at unchanged peripheral speed of cylinder. As a result of this, initial movement of air stalks are pressed more intensively with smaller cylinder diameter. So increase in the drum diameter, grain output of the threshing unit increases. So if we are increasing the drum diameter, grain output of the threshing unit increases. For that, what should happen? Wrapping angle should be greater than 90 degree. If wrapping angle is greater than 90 degree, then increase in drum diameter will increase grain output. And next thing is power requirement of thresher. So how we calculate power requirement of thresher? For that, we have a Goryachkin theory. Goryachkin drum theory is there, which is used to calculate power requirement of the thresher. So for this, we consider that the two like power requirement of thresher is consists of idle power and useful power. So idle power consists of this term like AU plus BU cube. So where A is the moment from frictional forces in bearing. This for a spike tooth it is 0.8 to 0.9, and for Rask bar it is approx I think 0.6, values is not given here, and factor B is 0.065, factor B 0.065 Newton second square per meter square. Screen is visible, Jigyas. Jigyasa, is my screen visible? So yes, we were discussing power requirement to overcome idle resistance. It consists of AU plus BU cube. And second is power requirement to overcome useful resistance. So this consists of, so this is the expression like power. This is force into F into force with which rasp bar strikes the crop material, and this is delta T. So, and mass of the crop material is m, and delta V is the velocity gained by mass of the crop. So this is the expression uh, for balancing both the term. Force into delta T is equal to mass into velocity. So both is power now. So this will become P is equal to m dot into V. So this is P1 is equal to F m dot V. And second is, in addition to impact of certain speed to the material, resistance of the concave offered during shifting of the crop material over it also occurs. So this is the friction term. So second term is friction, which is denoted by P2 is equal to F into P. So total resistance is given by P1 plus P2, which is m dot V plus F into P. So P will become m dot V. P is equal to m dot V plus Fp. So P will P will become 1 minus F equal to m dot V plus m dot V. So m dot V by 1 minus F is P. The power required is equal to this force into velocity. So this will be multiplied with velocity, and this will become m dot V square by 1 minus F. So total power required will become AU plus BU cube, which we have seen in earlier slide, and this is m dot V square plus by 1 by F. So this is the total power required. Now n is the power supplied by source, then n by n minus r, n by nr should be positive, which means and n minus nr is the, then speed of drum increases. If it is negative, then speed of drum decreases. It, it mainly deals with, if we want to have a better threshing, then moment of inertia should be more. That is, that has been discussed here in this slide. So it was found in the experiment that I1, I2 and I3 is the three thresher where I1 and I2 have both have were having same velocity u1, means I1 have velocity u1, I2 have velocity u1, and I3 is having velocity u2. U2 is having greater velocity than u1 and I2 is greater than I1, means I2 is greater than I1, means second thresher is having more radius. So from this graph it was found that for I2, this is for I2, d omega by dt is very less. This, and this is the requirement. So when d omega by dt is less, that is giving best performance. And in case of 3, you can see d omega by dt is very large. So it was concluded that bigger drum with lesser angular speed is preferred instead of smaller drum. So sharp change in speed imposes greater stress on working part and drive mechanism. So it is advised that thresher of drum should have larger moment of inertia. And next thing is threshing capacity. For rasp bar, threshing capacity is defined as QA into L into M, where QA is allowable feed rate. And in case of rasp spike tooth also, through this is threshing capacity. It is defined as this allowable feed rate, which is kg per second or kg per second per meter of length of rasp bar. This should be multiplied with number of bars in case of rasp bar and number of teeth in case of spike tooth. So in case of a spike tooth, through this threshing capacity is equal to QA into Z, where Z is number of teeth, and it is calculated using this equation MP into LP by A plus 1. So what is this MP, LP and A? Here we can see that LP is the length of working of drum, D is the drum diameter, and A is the distance between two adjacent paths, and MP is the pitch of helix. MP is pitch of helix, LP is the length of working of the drum, and A is the distance between two adjacent paths. So MP into LP plus A, LP by A plus 1. This is number of teeth. So from there we can calculate what is threshing capacity. Next thing is typical. This is the table for typical peripheral speed and clearance for various crops. For suppose rice and wheat, we can see for rice peripheral speed allowable is 23 to 28 meter per second and clearance should be given 5 to 10. So this table you can see. So next thing is terms associated with threshing operation. So these are the performance parameters for uh, of this threshing operation, for which first thing we calculate is percentage of damaged grain at all outlet. For that, damaged grain should be weighted for all outlet, and this should be divided with total grain input, that is B plus C plus D, which means B, where suppose B is weight of threshed grain, C is weight of threshed grain at outlet other than main grain outlet. B is for main outlet, C is for outlet other than main outlet, and D is for weight of unthreshed grain. So A will be sum of B plus C plus D. So damage percentage will be damage at all outlet by A. Second thing is percentage of blown grain. So whole grain at Busa outlet by A. This from here we can calculate blown grain, and percentage of grain loss. So grain loss is weight of threshed grain like if it is not coming at main grain outlet and if it is unthreshed, then it is grain loss. So C plus D by A will be grain loss. Percentage of unthreshed grain will be amount of unthreshed grain by total amount of grain. Threshing efficiency will be 100 minus unthreshed grain efficiency. Similarly, cleaning efficiency, whole grain or clean grain at main outlet by A. Percentage of spilled grain, optimal input capacity, output capacity, these are theoretical terms you can see. So next thing is corrected output capacity. So if it is used to compare performance of two or more thresher. If we want to compare, if we need to compare more than like one thresher with second thresher, then we need to know in one term which is corrected output capacity. If W is the output capacity of one thresher, we need to make it in terms of corrected output capacity. For that, we need to convert it with respect to moisture content of 12% and grain to store ratio of 40%. For that, we will use this formula and we can calculate corrected output capacity. So we are now in a position to solve the numericals of or the questions of week 12. So first question is, for threshing wheat crop with a spike to thresher, the peripheral speed of drum required in meter per second. So yes, you are saying B. So yes, from this table you can we can see that for wheat it is 25 to 30. So for wheat crop it is 25 to 30 meter per second, and here it is coming under option D. So yes, D is correct. So second question is, with increase in concave gap in a thresher, what will happen? Amount of threshed grain decreases. Amount of threshed grain decreases. You are saying option A. So when concave gap is, what is the question? Increase in concave gap. So we have just discussed that. Yes. When the concave gap increases, amount of threshed grain decreases and amount of damaged grain also decreases. So yes, option A is correct. The next question is, which of the following parameter affects performance of spike tooth thresher? So we have seen shape of tooth will affect, grain to straw ratio will affect, all of this. Okay. Peripheral speed of the drum will also affect. So all of this is correct option. So next question is, increase in drum diameter. The grain output of threshing unit increases provided the wrapping angle of the concave at the center of drum in degree is more than 90. Yes, we have just discussed that if wrapping angle is more than 90 degree, then this condition follows. So next question is, in a solar energy operated thresher, size of solar panels required for operating the thresher depends on. So this we can just uh, all. So yes, it will depend on torque requirement for carrying out threshing, duration of operation of thresher, availability of solar radiation throughout the day. Yes, this all factor will affect the power requirement for calculating the solar panel size. So all of this is correct answer. The next question is, a total power required by thresher for carrying out threshing of any crop includes power required to overcome what? Bearing friction, air pumping, friction between plant mass and components of thresher, as well as detaching of the straw. So what option you are telling? Yes, here also option will be D. So all of these is correct answer. Next question is, permissible feed rate of a spike tooth threshing cylinder having length of 1200 mm is 0.03 kg per tooth, kg second, kg per second per tooth, and distance between two adjacent paths is 100 mm. If the number of crossbar is 6, the threshing capacity of cylinder in kg per minute is. So we have just now discussed that threshing capacity is equal to QA into Z, and Z is equal to MP into LP by A plus 1. So QA is the allowable feed rate, which is 0.03 kg per second per tooth. So QA is 0.03 kg per second, and MP is the number of, so MP is pitch of helix, and A is the distance between two adjacent paths. So number of cross bars is 6. So number of pitch will be 6 by 2, and LP is the length of this cylinder. So a length is given, length cylinder having length is 1200 mm, and A is the distance between two adjacent paths, which is 100 mm. So we can calculate this as you are saying, Z is equal to 39. So Z will become 39. Okay, we can see here 3 into 1200 by 100 plus 1. So 13 into 3 is 39, and this arrival feed rate is 0.03 kg per second. So this into 60 we need to do to make it in kg per minute. So this into 60. So what you are getting? 1.17 kg per second. 70.2 kg per minute. So option B is the correct option here. 70.2 kg per minute. Next question is, the throughput capacity of a thresher was 180 kg per minute when moisture content of grain and grain to straw ratio is 12, 18 and 50% respectively. So corrected output capacity. So just now we have seen corrected output formula is W1 is equal to W into 1 minus moisture content minus 12 by 88 into 40 by R. So what is the moisture content here in grain to straw ratio here? It is 18 and 50, and 180 kg per minute is the throughput capacity of this threshold. So our corrected output capacity we can calculate directly. 180 into 1 minus 18 minus 12 by 88 into 40 by 50. Yes, yours correct. So what you are getting? 134.18. So option B is correct. 134.18. The next question is, a total grain input to a stationary power thresher is 1 kg per second. Quantity of both whole and broken grain collected at main grain outlet is 750 gram per second. Quantity of both whole and broken grain obtained from sieve overflow, sieve underflow and bhosa outlet is 50 gram per second. We are asked percentage of unthreshed grain. So percentage of unthreshed grain will be unthreshed grain at all place by total grain input. So total grain input, we need to convert it in one unit. First, this is 1000 gram per second. Suppose this is, and quantity of both whole and broken grain collected. So 750 gram per second. Yes, you are saying D is equal to A minus B plus C. That is 1000 minus 800 is equal to 200. So yes, you are correct. We can use that above formula also. D is equal to A minus B plus C. Or you can also think that 750 gram per second is both whole and broken grain. So this is actually threshed grain. This 750 gram per second is threshed in terms of both whole and broken. And quantity of both whole and broken grain in all other outlet is 50 gram per second. So total threshed is 750 plus 50, that is 800. So unthreshed grain will be 200 grams per second, and total grain input is 1000 gram per second. So unthreshed ratio will become 200 200 by 1000, which is 20%. So C is correct. So next question is, in order to reduce stresses on working parts of the thresher due to sharp changes in the speed of cylinder, it is advisable to have thresher cylinder off. We have just discussed it above. In order to reduce stresses on working parts of the thresher due to sharp changes in speed of cylinder, we need to have a cylinder of larger moment of inertia. From the graph, from that figure, we have seen that larger moment of inertia is advised for reducing stress. So yes, uh, I hope this week is clear. These are some of the questions. If you want to solve, then we can solve it here. Throughput capacity is being asked. Same question it is there. This question is based on Goryachkin drum theory. So we can solve this question. Then we can end the class. So following the Goryachkin drum theory, find the power requirement of a thresher with raspa type cylinder of length 110 centimeter used for threshing wheat at a cylinder peripheral speed of 28 meter per second. Feed rate of the grain is 3000 kg per hour and coefficient of material ribbing is 0.7. Assume velocity of the grain as 80% of the peripheral velocity of the drum. We need to find what is the power requirement. So power requirement, we have discussed that it comprises of Ni plus Nu, and Ni is Au plus Bu cube plus this useful force is m dot v square by 1 minus f. So what all things are given here? U is the speed of cylinder. So U is peripheral speed of the cylinder, which is 28 meter per second. U is 28 meter per second. M dot mass inflow is, mass of grain input is 3000 kg per hour. 3000 kg per hour. We can convert in kg per second, which will become 3000 by 36 kg per second. V is peripheral. Assume velocity of the grain, velocity V is velocity of grain, which is 80% of velocity of drum. So V is equal to 80% of U. 80% of 28 meter per second is 0.8 into 28. Coefficient F is coefficient of material rubbing, which is 0.7. Mainly you need to know A and B. So A is 0.8 to, I think it is between 0.8 to 0.9 for this rasbar type cylinder. So A is equal to 0.8 you can take, and B we can take 0.005. This is from standard notice, from standard values. So from here we can calculate what is the power requirement. So can you calculate, Jigyas? Calculate it based on these values and tell the answer. Zero 0.65. Okay, we can take 0.65. So A, B, U, M dot, V and F, all values are given. 334.188. So yes, this is in watt I think it will be. So in kilowatt we can write it as 3.3 kilowatt is the power requirement. So this is all for last like week 12, and if you have any doubts in this week or lectures, you can discuss, or related to any assignment questions we can discuss. So you can speak, Jigyasa, I think.
So, am I audible now? So, am I audible now?
Hello.
So, is my voice coming? So, am I audible now?
One minute. Hmm. Now you can say.
So, am I audible now?
Yes, you are audible.
Sir, in this week we have got like two more questions. New question was there. The power required by a thresher with zero yield is an indicator of power required to overcome. So that question, like both bearing friction and air pumping will be there, no? Like
Yes, yes. This question, right?
current
Hmm.
both air friction. No,
Yes.
this is like one
Hmm.
more C is there, but in this
Okay, bearing friction is
there,
not there.
one more question is there. A spike tooth harrow is fitted with solid circular section spikes during threshing of wheat crop. In this thresher, the spikes are subjected to torsion, bending, shear, and both bending and shear. So only bending will be there, no?
Bending
In
and shear, what all options are there?
it is spike tooth harrow,
Hmm. Spike tooth
and
harrow.
हाँ इस मतलब वो सेवेंथ वाले में हैरो ही लिखा था मतलब उसमें हैरो पता नहीं क्यों मतलब
It's
इट शुड बी
in week
टूथ
12.
एक्चुअली
In week 12 question.
हाँ like this
Harrow
week
question is there.
हाँ this week question only we have got like a spike tooth harrow is fitted with solid circular section
Hmm.
during threshing of wheat crops. In this thresher the
This
spikes
harrow is misspelled, means typo it is.
हाँ मतलब कि वो स्पाइक टूथ ही है वो थ्रेशर जो है स्पाइक टूथ है और उसमें सॉलिड सर्कुलर सेक्शन स्पाइक्स है एंड ड्यूरिंग थ्रेशिंग ऑफ व्हीट क्रॉप्स इन दिस थ्रेशर the spikes are subjected to option A torsion, option B bending, option C shear, and D both bending and shear.
Bending and shear should be there, I think, because shear is also taking place here in the spike too.
So not only bending won't be there.
Only bending only bending will not be there. Bending and shear, I think it should be there. So okay, I
Okay,
will
sir.
cross verify it. Okay.
Okay, sir. Okay. This
Hmm.
much only. Rest, sir, actually, I've submitted it already, but yeah, we have
Oh.
like 2 more days.
So in these 2 more days, you can submit it as many times. Na?
Again,
That's all.
again, I can submit it.
Hmm. So any more doubts from previous weeks?
No, sir, up till now it's okay. Like now on Sunday we have our exams.
Okay. Okay, then give all the best for exam. And this was the last week, so we will end this session, doubt solving session of this NPTEL course. And all the best to all of you for the exam. Okay, then I will end this class.
Okay, sir. Thank you, sir.